Good evening, everyone.
Good evening, ma'am.
Yeah, let's wait some 2-3 minutes for others to join. Okay, I think let's start the session. So today we will cover the week 6. So we will just go through the main concept and then we will solve some problems as usual. So let me share the screen first. Is the screen visible for everyone? And am I audible clearly? Okay. So first let us go through the main concept that covered in the last week, means week 6. So week 6 started with just one theorem. So let me just state the theorem. If W is a subspace of V, then dimension of W is less than or equal to dimension of V. So this is the one of the basic result. If W is a subspace of V, dimension of W is less than or equal to dimension of V. And okay, the proof of this is already covered in the class, so I'm not going into the details. And one of the main important theorem we have covered is if U W are subspaces of V, then dimension of U plus W equals dimension of U plus dimension of W minus dimension of U intersection W. So what it says is if U and W are two subspaces of V, and we know U plus W is the set of all elements U plus W, where U from U and W from W. Then U plus W is also a subspace and its dimension is given by dimension of U plus dimension of W minus dimension of U intersection W, where U intersection W is also a subspace. Okay. So, okay, after that, we have gone to the linear transformation. Okay, what is a linear transformation? Can anyone tell what is a linear transformation? Can anyone say what is a linear transformation? Given two vector space UV, linear transformation is basically a map, like transformation. Okay. T from U to V. It is a map from U to V, which satisfy some conditions. Can anyone say what are all the conditions for T to be a linear transformation? Am I audible to all of you? Okay, if you don't know also, like you can just tell. We can just go through what is a linear transformation.
T of A alpha plus
Yeah.
B beta
Yes.
where alpha comma beta belongs to U.
T of A alpha plus B beta equal to something, right?
Yes.
Yeah.
T of A into T of
No, A is the scalar. Like here alpha and beta, we are taking as vectors from U, and A and B are scalars. Okay. So A into T alpha. Okay. So A alpha plus B beta, where alpha, beta are vectors. So A alpha plus B beta is also a vector. If we are applying T on this vector, it should be equals A into T applied on the vector alpha plus B into T applied on the vector beta. Okay. This is the meaning of linear transformation. This should be true for all alpha, beta in the space U because T is from U to V. Alpha, beta in U, and also for all A, B scalars, like whatever the field. Okay. Under which field this U is defined. Like in that, from that field, we will take the scalars. Okay. So this is the condition. Like either we can tell like this, or we can tell that like we here what we are having is addition, vector addition we are having, and also scalar multiplication also we are having. So instead of writing it combinedly, we can write it separately also. In the way T of C alpha equals C into T alpha, and T of alpha plus beta equals T alpha plus T beta. Okay. If these two conditions are together satisfied, then also like what we are doing is just separating this condition to two conditions. Otherwise, we are combining these two conditions to get this condition. Okay. So both are equivalent. If either of this is proved, we can say T is a linear transformation. Okay. Is that clear for everyone? What is a linear transformation?
Yes, ma'am.
Okay. So this is the one of the main thing in the last week. Like we will be checking what is like if a given map is given, we will be checking whether it is a linear transformation. Okay. So many of the concept like following is depending on this linear transformation. So first of all, you should understand the linear transformation clearly. Now, what is kernel of T? So T is a linear transformation we have already defined. What is kernel of T? Anyone knows what is kernel of T? Or otherwise, we will say this as null space of T. Anyone knows what is null space of T? Okay, null space of T means the set of all, like we already know, T is from some vector space U to V. Okay, so T maps elements of U to V. So null space means set of all elements in U which are mapped to 0 element of V. Okay, that means set of all alpha in U such that T alpha equal to 0. So what are all the elements from U go into V that constitute the null space? Okay. Is this clear? What is null space or kernel of T? And this kernel of T is okay. T is mapped from U to V, and the kernel of T is the set of all elements from U which maps to 0. So what we can say, kernel of T is a subset of U because it collects the elements from U which maps to 0. So it is a subset of V, subset of U, but we can prove that kernel of T is a subspace of U. For the proof, you can go to the lectures. I'm just stating the result. Okay. This kernel of T will be a subspace of U, means it itself is a vector space. Fine. And one more thing here to notice is nullity of T. Anyone knows what is nullity of T? Can any guess what will be the nullity of T? Nullity of T means it is related to the null space of T. Any idea?
It is the dimension of the null space.
Yes, it is the dimension of the null space. We already proved that, like we already stated that this is a subspace of U. So subspace means it itself is a vector space. So it will have some dimension. Okay. So what is the dimension of the null space? So that is called the nullity of T. Okay. Now let me state one result. T is 1, 1 if and only if kernel of T equals 0. Okay. Again, I am not giving the proof. Here what it says is T is 1, 1. 1, 1 we know 1 to 1 map. This T is a 1, 1 map if kernel of T equals 0. Kernel of T, we told it is a subspace of this U. Okay. If that is, we are getting kernel of T as 0, we can say T is 1, 1. Okay. Conversely, if T is 1, 1, we can say that the null space of T is the trivial space 0. Is that clear? Any doubt until now? Okay, just understand the concept because like without that, we cannot move to the problems. And if you have doubt here, like in any of the concept or you want me to explain once again, you can just tell. Now, image of T or range of T. Okay, from the name, image or range itself, you can guess what will be it. What will be the range of T or image of T? What is the meaning of image? Like T is a map, and what is image of T?
V, ma'am.
Will it be V always? Like we know T is from U to V. Okay. But image of T means the set of all elements, like which can be obtained under the map T. Okay. That only we will say image. So for any map, for any function f we are taking, if we have f here, 1, 2, 3, 4, 5, something like this. And 1 is mapping to 2, 3 is mapping to 4, and 5 remains like that. Like it is not mapped. So in general, the image of F means only 2 and 4, right? 5 is not there. That means it is not the whole space. Like what are all the elements which is mapped under the map? So that is our image. Here also the same concept. In general, for a function, it is the image or range. So in this linear transformation also, we can say image of T equal to set of all T alpha such that alpha in U. So we are taking all elements in U and we are finding all the value T alphas and collection of all that T alpha is the image of T. Okay. Now again we can see image of T is a subset of V. As we already told, it contains all T alpha. That means T alpha means it is image elements in V. Okay. Actually, it is not just a subset, it is a subspace of V. Image of T is a subspace of V. Note that kernel was a subspace of U because it was the set of all elements which are mapped to 0. It was a subspace of U. And here it is a subspace of V. Okay. And now again, rank of T. Here we told it is a subspace of V. So for this subspace, some dimension will be there and that dimension is called the rank of T. Dimension of image of T is the rank. Okay. Like, is this clear for everyone? This linear transformation, null space, nullity, range, rank, everything is very important while solving problem. So if you have any doubt, please ask. And if you want to explain any concept once again, you can tell. Any doubt here in any of this? Is everything clear for everyone?
Yes, ma'am. We can go to problem, ma'am.
Okay. Now, one of the important theorem and that we will be using while solving the questions is rank nullity theorem. Anyone knows what is rank nullity theorem? So we stated what is rank and what is nullity. Okay. So obviously, by then, as the name suggests, it is the theorem involving both rank and nullity. And T is a map from U to V. Anyone knows what is rank nullity theorem? It is the very important result in linear algebra. So, yeah, the question is here, how to write the linear transformation in matrix form. So while solving the problem, we will come to those kind of questions. Okay. So first, let us just go through the concept. Otherwise, like while doing the problem, it will be a bit difficult to understand. So, anyone knows rank nullity theorem? Okay, what it states is rank of T plus nullity of T equals dimension of U. Here, T is a linear transformation from U to V and rank of T means the dimension of the range of T and the nullity of T is the dimension of the null space of T. Okay, and the result states that if we are adding those two dimensions, that is rank of T plus nullity of T, we will get the dimension of this space U. Okay, That means dimension of M, just rewriting it in different words, okay? Dimension of range of T plus dimension of null space of T equals dimension of U. Clear? This is our rank nullity theorem. Just remember this theorem. We will be using this throughout the session. And some more theorems like, okay, some more theorems also we have proved in the class. You can just go through the lectures. And so what else we have studied in the last week is composition of linear transformation. I'm not going to the details of this. One thing is it is very trivial. Like composition means we already know what is the composition of two functions. Just like that, we can say what is the composition of linear transformation. Like S and T are two linear transformation. What will be S composition T? And from where to where it is defined and what. It is just as the usual function composition. Okay. And inverse of a linear transformation. Suppose T from U to V. Okay, U and V are two vector space and T is a linear transformation from U to V. And if T is bijective, then T inverse exists, right? If T is a bijective map, it is 1, 1 and on 2. So obviously some T inverse map existed. So that T inverse is called the inverse of T. Again, it is the usual definition of the function inverse. Now what we can say is here between two vector spaces U and V, if a bijection T existed, then we can say U and V are isomorphic vector spaces. So isomorphism between two vector spaces. So this is just saying that if the T map, if the linear transformation T is a bijection from U to V, then U and V are isomorphic. Again, one more important theorem is so in the case of finite dimensional vector space, what we can say is if U, V are finite dimensional vector space, and dimension of U equals dimension of V. Okay, what it says is U and V are finite dimensional and both the dimension, like dimension of both U and V are same, then this U and V are isomorphic. Is this clear? The only thing we are saying is if this, like if U and V are finite dimensional and both the dimensions are same, then this U and V are isomorphic. So one of the important corollary from here we can see is if U has dimension n, suppose U is a vector space and its dimension is n, then we can say that U is isomorphic to Fn for any field F. Okay, so this is just the corollary of this theorem. Here, what is Fn? F is a field, so Fn is a vector space over F. Here, dimension of Fn will be, for example, instead of S for simplicity, we can take R. Okay, so U should be isomorphic to Rn. What is the dimension of Rn? What is the dimension of Rn?
Dimension of U, ma'am.
No, I am asking, okay, it is dimension of U because it is isomorphic. I'm asking what is that number? What is the dimension of R? Yeah, N. Dimension of Rn is N. So what I am trying to say is how we are using this theorem for this corollary. So here dimension of Rn is N and it is given that U has dimension N. So here what we are getting is U and Rn are finite dimensional vector space and its dimension both are equal and which is equal to N. So U and Rn are isomorphic. So that is why U and Fn or U and Rn are isomorphic. Okay. So in general, what I want to say is if we are taking any finite dimensional vector space, we can say that space is isomorphic to some Rn depending on the dimension of the space. Okay. Is this clear for everyone? This one? And okay, let me give the last one. What is the space? LUV. LUV is the space of all linear transformation from U to V. Okay, so you can just check that whether this forms a vector space. Set of all T from U to V such that T is linear. Okay, so LUV is the space of all linear transformation. So it is a vector space. You can just check all the properties of the vector space, whether it satisfies or not. So these are all the things that covered in the week 6. So I hope we have gone through almost all important concepts. And if you have any doubt in concept, we can just clear the concept or just I can tell once again. Otherwise, we can go to the problems. Any doubt here in any of this result or definition or anything? Okay, so before moving to the problems, here we have one question. What is the difference between a linear transformation and a function? Okay, so linear transformation, as we already stated, it is a map from a vector space to a vector space which satisfy T of Cx plus y equal to C into Tx plus Ty. Okay. T from U to V such that T of Cx plus y equal to C times Tx plus Ty for all xy in U and C in the field F. Okay. So linear transformation means it should be a map from U to V and it should satisfy this condition. But for a function, we don't have any such restriction. A function can be defined on any set. A function F can be defined on any set. Okay, it need not be a vector space. Linear transformation is defined on a vector space first of all, and it is defined on a vector space and it is going to a vector space. But for example, a function can be defined from a set 1, 2, 3 to some set ABC. It is not a vector space also. Okay. So first difference is that a function is a very generalized form of linear transformation. Okay. And one more thing is T satisfies this linearity condition. But a function in general need not be satisfy this linearity. First of all, this linearity comes just because this is defined on vector space. Like we can add this addition, multiplication, everything we can do just because we have a vector space with two operations, vector addition and scalar multiplication. Here in the set, we don't have any kind of operation. So this kind of things is not at all possible. It is just a mapping. It is just an assignment to each of the element of the domain and an element from here. Okay.
Okay, ma'am.
My screen is visible now, right?
Yes, ma'am.
Okay. So yeah, the function is just an assignment. It need not satisfy this condition. Okay. And one more thing, suppose T from R to R. Okay. With T of X equal to X square. Is this a function? First question. T is a map defined from the real line to real line. And T of X is defined as X square. Is this a function? Okay, this is very trivial question. Anyone can answer.
Yes, ma'am.
Yeah,
It is a function, ma'am.
And is it a linear transformation?
No, ma'am.
No. You can just take any example. For example, I am taking T of 1. Okay, 1 is a vector. And what is T of 1 equal to 1 square, which is 1. Okay. And T of some 3 into 1 I am taking. 3 is a scalar. Okay. T of 3 into 1 equal to T of 3, which is equal to 9. And what is 3 into T of 1? Here 3 is a scalar. If T is a linear transformation, T into 3, 1 should be equal to 3 times T of 1. But here 3 times T of 1 equal to 3 into 1, which is 3. Okay. So here what we are getting is T of Cx not equal to C times Tx. Here C equal to 3 and X equal to 1 I am taking. Okay. So this condition is not satisfied. So it is not a linear transformation. So what I am saying is, even though function is defined on vector space, still it need not be a linear transformation. It should satisfy the desired conditions. The condition we stated above, that the multiplication and the linear with respect to multiplication and the scalar multiplication and the vector addition. Okay. So as someone stated, any linear transformation is a function, but a function is not a linear transformation always. Okay.
Okay, ma'am.
So let us go to the questions. So first question is to check whether the given maps are linear transformation or not. So which of the following Mappings are linear transformation. So while I write the question, you can just try to solve your own. So if you are trying to solve your own, you will get to know what is the problem, like where you are finding difficulty and all, and you can ask the doubt. So just check the first question, whether it is a linear transformation or not. Okay. So what about the first question? What is your guess? Is it a linear transformation? Actually, just by examining itself, we can say some map is linear transformation or not. Like in the name itself, it is written linear, means it should be in the form of linear functions. So what is your guess about the first transformation T1? Any guess? You can just like just make a guess actually.
No, ma'am.
No. Can you tell the reason also? Or any counter example like why it is not linear? The thing is, if it is not linear, obviously it is a map from a vector space to vector space. So if it is not linear, it is not satisfying one of the condition. That is either T of Cx equal to C into T of X or T of some X plus Y equal to Tx plus Ty. Any of this condition is not satisfied. So what is the reason? Anyone?
T of Tx condition, it does not satisfy.
T of
Cx.
Okay, T of Cx need not be equal to C into T of X. So the
Yes.
thing is, here the quadratic term comes. Quadratic term comes means everything is like this C is also getting squared. So just as the earlier example, here we have seen T of X equal to X square. The same problem happens here also. Here what happens is, inside T, if we are getting this 3 is getting squared. But here, if we are taking outside 3 outside, then 3 remains as it is and 1 is only getting squared. So we are getting only 3. So the same problems happens here also. For example, what will be T of 1, 0, 0? Okay, T of 1, 0, 0. Here, the function is T of x, y, z equal to x square plus y square, z square. So T of 1, 0, 0 equals 1 and 0. Okay, x square plus y square is 1, z square is 0. Now, I'm doing T of 2 times 1, 0, 0, which is T of 2, 0, 0. Okay, here we will get 4, 0. You can do the calculation. T of x, y, z is x square plus y square, z square. Now, let us check 2 times T of 1, 0, 0. That means T of 1, 0, 0, we have already found it is 1, 0. So, we will get 2 times 1, 0, which is just 2, 0. Okay. Basically, not just T of C, like T of Cx equal to C into T of X is not satisfied. In the same way, T of X plus Y equal to T of X plus T of Y also will not be satisfied because X square plus Y square is not equal to X plus Y whole square, right? So you can just check that condition also. Okay, not just this condition, the other one also will not satisfy. So just using this condition, very simple example, we can say this T is not linear. Okay, so as I mentioned earlier, to check the linearity, means just by inspection we can say it is not linear because some quadratic terms comes. Okay, in the same way, if some cubic terms or something like x cube or something comes, then also we can say it is not linear. It should be some linear combination. Linear combination means like this 5x plus 3y, like this it is coming, right? Linear combination we have already studied. So if linear combination is comes, that means power is always 1, then only it will be a linear transformation. So is the first question clear for everyone? This first example. Any doubt in the first example why it is not a linear transformation?
No, ma'am.
Okay. Now, what about the second one? Is the second one linear or not? As I already mentioned, it is all just linear terms. So it should be linear actually. But we should check. Like if it is not linear, we have given one case where the linearity property is lost. So in the same way, here, if it is linear, we should prove in general both the conditions are satisfied. So let us see. So first of all, because it is a just linear combination, we can intuitively we can say it is a linear transformation. Now we are going to prove it explicitly. For that, okay, let me write it. T2 is defined as T2 of xyz equals 5x plus 3yx.
No, ma'am. It's not. It's also not linear.
Reason?
This is also not satisfying the condition T of Cx is equal to C times of Tx.
Okay, let us check once. Okay.
Okay.
What we want to prove check is T2 of C x, y, z, whether it is equal to C times T2 of x, y, z. Okay, this is our question. So we will start with the T2 of C, x, y, z. C, x, y, z means Cx, Cy, Cz. Okay, C times Z upward. Now we will apply the definition of T. So what we will get is, instead of x, we have Cx here. Okay, so 5 times Cx plus 3 times, instead of y, we have Cy here. 3 times Cy. Okay, next one is x. X means here it is Cx. Cx. And third term is 2y minus 5z. Here y is Cy. So 2 times Cy minus 5 times Cz. Okay. Here in both the term we have C. So we can take this C outside. C times 5x plus 3y. C times x. C times 2y minus 5z. Again, C is there in each of the coordinate. We can take C outside. 5x plus 3y. X. 2y minus 5z. Okay. So, what is this 5x plus 3y x 2y minus 5z? So this is T2 of x, y, z. Okay. This is what we got here. This is T2 of x, y, z. So we can write it as C times T2 of x, y, z. So we have taken the C outside here. So this condition is satisfied. Okay.
Ma'am,
Yeah.
if we take x equal 1 and y equal 2 and again z equal 1, this condition not satisfied.
Okay, we can
I-
check. X equal to 1.
If we are giving the value
Yeah, can you repeat the value?
x equal 1, y equal 2 and z equal 1.
Z equals 1.
Yeah.
And what is C?
2.
Okay, C equal to 2. So first we will see what is C x y z. That means 2, 1,
4,
2,
2.
1.
Okay.
Okay, so 2, 4, 2. So T of C x y z equal to T of 2, 4, 2. Okay. So by definition it is 5x plus 3y. So 10 plus 12. 22 and x 2y minus 3z. Sorry, 2y minus 5z minus 2. Correct? Okay, just check the calculation also, my calculation. And C times T of xyz equals 2 times T of 1, 2, 1. So 5x plus 3y, which is 11.
Sorry, ma'am, it satisfies.
Yeah, it will satisfy actually. Like we
Yeah,
have
yeah.
proved it in general. So
Okay.
it will satisfy. Now, okay, let me complete it. Second term is x and third term is 2y minus 5z. 4 minus 5, which is minus 1. Okay. This is also 22, 2 minus 2. Okay. So, okay, only thing is if the things are coming linear, like terms are all linear terms, obviously it will be a linear transformation. Here we have proved it in general, like how we are taking the C outside, step by step we are taking the C outside and this condition is satisfied. Now let us quickly go through the second condition also. So T2 of x1, y1, I'm taking two elements, x1, y1, z1 and x2, y2, z2. So what I want to prove is it should be equal to T2 of x1, y1, z1 plus T2 of x2, y2, z2. Okay. So, sorry, here it is plus. So, we will start with this side. T2 of x1, y1. Okay, let us very quickly go through it is just a computation and a rearrangement. So, it will be T2 of x1 plus x2, y1 plus y2, z1 plus z2. Now we apply the definition to this. Okay. This is 5x plus 3y. Instead of x, we have 5x1 plus x2. 5x1 plus x2 plus 3y. Instead of y, we have y1 plus y2. Next term is x. Here x is x1 plus x2. And third term is 2y minus 5z. So here 2y1 plus y2 minus 5z1 plus z2. Now what we want is we need to separate it as T of x1, y1, z1 plus T of x2, y2, z2. So in that way we will separate this term. So T of x1, y1, z1 will be 5x1 plus 3y1, sorry, 5x1 plus 3y1, x1, 2y1 minus 5z1 by definition. So we can separate it as 5x1 plus 3y1. So I'm taking 5x1 plus 3y1 from the first term. From second I am taking x1 and 2y1 minus 5z1. Okay. And the remaining term I am taking to the second. Okay. 5x2 plus 3y2. And here x1 we have given here. So x2. And here remaining is 2y2 minus 5z2. Okay, I'm just separating it accordingly so that I will get t of x1, y1, z1 plus t of x2, y2, z2. Now you can see this is t of x1, y1, z1. By definition, you can check this is the value t of x1, y1, z1. This is just a rearrangement only. I hope you are following. T of x2, y2, z2. Okay. Is this clear? How we have proved this linearity in this case? Any doubt here?
No, ma'am.
Okay.
No, ma'am.
So we proved that second one is T2 is a linear transformation. So someone has asked a question, how we can how can we write the linear transformation in a matrix form? So let us do that question with this example. So let me write the linear transformation. Okay, instead of T2, I am writing just T for simplicity. So Txyz equal to 5x plus 3y x 2y minus 5z. Okay, this is our linear transformation. Now the question is to find the matrix form. What is the matrix form of T? Okay. So for a matrix form, we will choose, we will fix some basis. Usually we will fix the standard ordered basis. Okay. So, okay, before going to the detail, anyone knows how to write the matrix form, or anyone can write the matrix form of this transformation? If you can just tell, and then we will go to the explanation. Okay. In general, how we will, if T is a linear transformation from U to V, and let V1 equal to some alpha 1, alpha 2, etc. alpha n is a basis of U, suppose. And V2 equals beta 1, beta 2, etc. beta m. Here, U has n elements in the basis and V has m elements in the basis. Okay. Basis of V. How we will generally write the linear transformation. What we like the matrix form of the linear transformation. What we will do is we will apply T to all the elements in the basis of U. And then we will get an element in the V. Okay. So that element can be written as a unique linear combination of elements of the basis of V. Okay. So the coefficient of that linear combination will be taken as the column. For example, I will first do T alpha 1. Okay. So T alpha 1, suppose I am getting it as some, say X, something I am getting in general. Okay. Now, T is a map from U to V. So alpha 1 is an element in V. and T alpha 1 is an element of V. And for V, we have a basis beta 1 to beta m. Okay, so we can write this X element as the linear combination of the elements of the basis. So if I am writing it as A11 beta 1 plus, that means the linear combination of elements. A21 beta 2 plus etc. AM1 beta m. Okay, so this representation is actually unique. So using this representation, we will get a coefficient, m coefficient, A11, A21, etc., AM1. So this A11, A21, etc., AM1, it will be the first column of matrix of T. Okay, matrix representation of T, the first column is given by this coefficient. And this matrix usually we will write it as TB1, B2. Means this matrix is written with respect to this basis. We are taking the image of elements from this basis, and whatever the image, we are writing the linear combination of elements of this basis. Okay, so B1, B2 are involved in this. So we will write it as TB1, B2. So for alpha 1, we got like this. Okay, now T alpha 2 is some element. Again, we will write A12. So as the linear combination, like T alpha 2 is an element in B. So we will write it as a linear combination of the basis B2. So A12, A22, beta 2, plus etc. AM2, beta m. Okay. Now, whatever we got the coefficient is the second column. A12, etc. AM2 will form the second column of the matrix T. Okay. Like this, we will proceed, and whatever the T alpha n coefficient, so we will write a T alpha n, and whatever the coefficient we are getting, we will write it as the nth column. Okay, you can just work it out. So what we will get is, so these are all the rows. Okay, this is the first column, this is the second column. So how many rows it will have? Like corresponding to each alpha 1, alpha 2, etc., alpha m, alpha 1, alpha 2, etc., alpha n gives n columns. Okay, means alpha 1 gives one column, alpha 2 gives next column, etc. Alpha n will give the nth column. Okay, so the matrix T will have n column. And how many rows it will have? How many rows will the matrix T will have?
M rows.
M rows, because here we can see 1 to m it varies. Okay, it will have m rows. Okay, so the matrix of T is an m by n matrix. M by n matrix. Okay, and what is m? M is, we have taken as the number of elements in B2. That is, B2 means beta 1, etc., beta m. And n is the number of elements in B1. B1 is the basis of U, and B2 is the basis of V. That means m is the dimension of V, and n is the dimension of U. So T is an m by n matrix with m equal to dimension of V and N equal to dimension of U. Okay. So this is the general way to write the matrix form. In general, like while taking the basis, we will take the standard basis. Okay. So now we will go to the our T map. Okay. So is this clear, like how I have written that matrix form? Is this clear for everyone?
Yes, ma'am.
Okay. Okay, then if you can very quickly say how the matrix will come here. So we can go step by step. So can anyone tell how we will start for the to write the matrix of T? Matrix of T to write, we should start with the basis. Any basis you can take. For simplicity, we will deal with the standard basis. So let B1 be the basis of R3. Like we have R3 means both the domain and codomain are R3. So here we have standard ordered basis for R3. So what is the standard basis of R3?
1 0 0 0 1 0 0 0 1.
Yeah. So we will take the standard basis 1 0 0 0 1 0 0 0 1. Okay. So the standard basis is taken for both of these R3. Okay. Now, what is the next step? Basis is same for both R3. Now, what is the next step?
Ma'am, we should take an element from R3 and try to write it as a linear combination of the elements in basis.
Okay, it is not just some random elements. We should take elements from the basis and write the image of that element in terms of linear combination of the basis. Okay, here what I'm saying is, earlier we have taken B1 and B2. B1 is a basis of the first space and B2 is the basis of the second space. Here we have both B1 and B2 are same. Okay, 1 0 0 0 1 0 0 0 1. Both are same. Now what we want to do is, we will apply the T map to each of this element. First we will apply to 1 0 0. Whatever we are getting, we will write it as the linear combination of these elements. Okay, so let me write that. T of 1 0 0. What is T of 1 0 0? T is this map. What is T of 1 0 0?
5, 5, 0.
5, 1, 0, right? 5, 1, 0. Okay, x equal to 1 here. Y, z are 0. So 5, 1, 0. Now what is the next step? We have found the image of the element 1, 0, 0 under T. Now we need to write it in terms of, we need to write it as the linear combination of the elements in the basis B2. That is basis of this R3. Okay, so how can we write it as the linear combination of these three elements? How can we write this element as this linear combination of these three?
5 into 1 0 0 plus 1 into 0 1 0 plus 0 into 0 0 1.
1 into 0 1 0 plus 0 into 0 0 1. So this is how we can write it as a linear combination. Now, can you tell what is the first column of T? First column of matrix of T.
5, 6, 1, 6.
Yeah, this is 5 1 0. We are just taking the coefficients from here, writing it as a column. That is our first column of T. Okay. Now, what is this? We have completed the process for the first element 1 0 0. Now we need to do the same for 0 1 0. Now, what is T of 0 1 0? We can go very quickly now. What is 0 0 1 0? This is the T map.
3
3 0 2.
0.
Yes. 3 0 2. Now, how we can write it as linear combination?
3 into 1 0 0
Yeah.
plus 0 into 0 1 0 0 0 1.
Correct. Now, what is the second column of the matrix?
3 0 2, ma'am.
3 0 2. Now, we can find T of 0 0 1. What is T of 0 0 1? Third element 0 0 1 we are taking. What is T of 0 0 1?
0 0 minus 5.
Yes, 0 0 minus 5. And how we will write it as 0 into 1 0 0 plus 0 into 0 0 minus 5 minus 5 into, sorry, 0 into 0 1 0 minus 5 0 0 1. And so third column is 0 0 minus 5. Correct? So what is the matrix T? We just need to write the column together. Okay. So first we got the column as 5 1 0. 5 1 0. And second column is 3 0 2 and 0 0 minus 5. Okay. Now, if you are seeing, like we have done this many work, actually we don't need, like I just want you to understand what is going on. So basically, if in competitive exam and all, we don't need to do all this work. Only thing we need to do is take the coefficient of x and write it in the first column, coefficient of y in the second column. So let me write the T map again here, so you will understand. T of x, y, z equals okay. So here you can see that what it actually happens. 5x plus 3y. So it actually in the order x, y, z, this coefficient is coming in the same order. 5, 3, z coefficient 0. Here x coefficient is 1. All other coefficient are 0. So this second and third elements are 0. Here also x is not there. So it is 0. 2y minus 5z. 2 and minus 5 are coming. Okay. So if you are getting a linear transformation, you can just write directly like this. Okay. Now, why the matrix T is the matrix form of T of x, y, z? Because if we are writing T of x, y, z, that is the usual matrix multiplication is 5 3 0 1 0 0 0 2 minus 5 into x, y, z. What we will get is 5x plus 3y x 2y minus 5z. Okay, this is exactly our linear transformation. So this is the reason why T is the metric, because if we are applying T to XYZ, we are getting this linear transformation. Okay, and if we are having a matrix, we can write the linear transformation, and if we are having the linear transformation like this, we can write its matrix form. Okay, is this matrix representation is clear for everyone?
Yes, ma'am.
Okay. If anyone has doubt, you can ask. Like we can clear that and then go. Okay. Now let's move to the next problem. What is M2 of R? Anyone knows what is M2 of?
Set of all 2 by 2 matrices
Yeah,
taking
set of all 2 by 2 matrices over R. Denotes the set of all and we have given a linear transformation from M2 of R to M2 of R. So linear transformation is given from the set of all matrices 2 by 2 matrices to set of all 2 by 2 matrices. So we are applying to a matrix T of A equals A minus A transpose by 2 for all A in M2 of R. So question is, what is the dimension of null space? And options are 3, 2, 1 and 4. Okay. Sorry, give me 1 minute. Sorry, there is some problem with this writing pad connection. Is the screen visible now?
Yes, ma'am.
Yes,
Yes, ma'am.
Yes, ma'am.
Okay, let me write the question once again quickly. So M2R, the space was M2R, and the map T was given from M2 of R to M2 of R, and it is given as T of A equal to A minus A transpose by 2. So the question was dimension of null space of T. Okay. So, and the answers were 3, 2, 1, and 4. Okay. So before going to the question, so we have already defined what is the null space and the dimension of null space. And for the dimension of null space, we have one more name, nullity, right? Nullity of T. So what is the null space? Do you remember what is the null space?
Yes, ma'am. The set of all elements which maps to 0.
Yeah, set of all elements from M2 of R which maps to 0. So null space of T equal to set of all A from the domain M2 of R such that T of A should be equal to 0. T of A equal to 0 means it is the 0 matrix. Here T of A is a matrix in M2 of R, means T of A is A minus A transpose by 2. It is again a matrix. Okay. So T of A is a matrix and equating it to 0 means it is a 0, 2 by 2, 0 matrix. Okay. Now the condition is T of A equal to 0. So let us just examine that one itself. Okay. T of A equal to 0. By definition, what is T of A? It is A minus A transpose by 2. So T of A equal to 0 means A minus A transpose by 2 equal to 0. Okay. What does this means? A minus A transpose equal to 0 or A equals A transpose. So what is actually the null space of T? Set of all A such that A equal to A transpose. A equal to A transpose means how can we call that matrix? What is the name of that matrix?
Symmetric matrix.
Yeah, symmetric matrix. Set of all symmetric matrix forms the null space for the given linear transformation. Now, our question is to find the dimension of this null space. Okay. So, dimension of this null space means null space is the set of all symmetric matrices, and dimension of null space means dimension of the symmetric matrices. Okay. So, I think in the last class we have done what is the dimension of symmetric matrix. Okay. Otherwise also, can you tell what is the dimension of this set, this space?
3, ma'am.
Yeah, it is 3. Let us just very quickly go why it is 3. A equal to A transpose. For example, if A equals A, B, C, D, I am taking. Okay. And A transpose should be equal to AB. Like rows and columns are interchanged. Here what we can say, A equal to A. There is nothing. Here next term, B equal to C and C equal to B. Second condition is B equal to C or C equal to B and D equal to D. So, if A equal to A transpose, then A is determined by the variables A, B and D. C should be equal to B. Okay. A, B. Instead of C, we can write B and here D. So only 3 variables A, B, D determines A. Okay. So the dimension of A, dimension of null space equals 3. So the last class we have mentioned this, like dimension is 3, and the basis also we have mentioned. Here the basis will come here 1 0 0 0 0 1 1 0 0 0 0 1, means taking 1 to 1 variable at a time, and all others are 0. In the second stage, B equal to 1, A, D equal to 0. And in the third element is D equal to 1, A, B equal to 0. So that 3 elements forms the basis. And so null space, dimension of null space is 3. Is this clear for everyone? Like how we have found the null space and how we found the dimension, or we can say it is the nullity of T. Any doubt in this question? Anyone? Doubt?
No, ma'am.
Okay. Now let me ask one question. What is the rank of T? Can anyone answer what is the rank of T?
1,
Same,
ma'am.
ma'am.
1. What is the reason rank of T equal to 1?
Dimension of V equal to rank of T plus nullity of.
Yes, we have the rank nullity theorem. What does that say? Rank T plus nullity of T equal to dimension of V. Here V is the M2 of R. Here what is dimension of M2 of R? M2 of R means set of all 2 by 2 matrices. It has dimension 4. Like 4 variables are there, A, B, C, D. So its dimension is 4. And we got nullity of T equal to 3. Nullity of T equal to 3. So rank of T plus nullity of T equal to 4. And hence rank of T should be equal to 1. That means rank of T means the dimension of the range of T, set of all elements in like set of all TA. That is the range space. So the dimension of that range space is rank of T, and we got it equal to 1. Is that clear for everyone?
Yes.
Okay. Then or you can find using the rank-nullity theorem. Otherwise, you can find using the definition also. Because like what I'm saying is, if you are taking set of all TA such that A in M2 of R. Okay. Now, we know what is TA. By definition, it is A minus A transpose by 2. Just expand that A minus A transpose by 2 and see how many variables are there. Like, or let me read it. So here T of A equal to A minus A transpose by 2. If we are taking A equal to A, B, C, D, then A transpose is A, B, C, D by 2. Okay. So which is equal to half into A minus A equal is 0 gone. Here B minus C, 0, B minus C, C minus B, and D minus D equal to 0. Okay. We can write it as 0 some K minus K 0, where K equal to B minus C by 2. Okay. So I'm just like, instead of this two variable, both are same. It is just the inverse of this one. So instead of B minus C by 2, if I am giving K, here I will get K, and here I will get minus K. So only one variable is involved in the range. T of A constitutes set of all elements in the range. So in this only one variable is involved. So from here also we can say dimension of range of T. Dimension of range of T equal to. Sorry, any doubt? Anyone has doubt here? If you are not talking here, then you can mute. Okay. If no doubt here, we can move to the next problem. Otherwise, you can any doubt?
No doubt.
Okay. Now let's go to the next problem. So if a linear transformation T is given from R3 to R2, So the question is, we have given a linear transformation from R3 to space R2. And it is given that it maps the basis vectors 1 0 0 0 1 0 0 0 1 2 the vectors 1 1 2 3 3 2 respectively. That means 1 0 0 is mapped to 1 1, 0 1 0 to 2 3, and 0 0 1 to 3 2. Okay. So the question is to find the value of t at 1 1 0. So okay. So how can we start with this question? How can we solve? Any idea? Any linear transformation is actually just based on the vectors in the basis. Like if we know the value of t at the basis, then we can write the t explicitly. Like the general form of t, we can write it. Here we don't need to write the general form. We just need to find the value of t at 1 1 0. First of all, what we should write is, we know the value of t at these 3 points. Okay. We know what is t of 1 0 0, t of 0 1 0, t of 0 0 1. It is given these values. Okay. So only thing we know is these 3 values, like value of t at these 3 values. So we should use that thing to here. We need to find 1 1 value of t at 1 1 0. So we should write 1 1 0 in terms of these 3 elements and find the value of t at 1 1 0. Is that clear? Is that clear what I am saying here?
Yes, ma'am.
No, ma'am. Could you please repeat it once, ma'am?
Okay. So here we know the value of t at 1 0 0 is 1 1. And the value of t, that is t of 0 1 0 is 2 3. And t of 0 0 1 is 3 2. Okay. And we need to find t of 1 1 0. So what we will do is, we will write this 1 1 0 as a linear combination of these 3. That is 1 1 0 equal to some a into 1 0 0, b into 0 1 0 plus c into 0 0 1. Then we will apply t of 1 1 0 equal to t of that linear combination, and then we will use this thing, like t of 1 0 0 is 1 1, t of 0 1 0 is 2 3, and t of 0 0 1 equal to 3 2. This is the general procedure. Okay, I think, okay, let me write that, then you will get to know it clearly. How we can write this 1 1 0 as linear combination of these 3 elements?
1 into 1 0 0 plus 1 into 0 1 0 plus 0 into 0 0 1, ma'am.
0 into 0 0 1. Now, instead of writing t of 1 1 0, what I can write? T of 1 into 1 0 0 plus 1 into 0 1 0 plus 0 into 0 0 1. That is what I am saying. Writing it as the linear combination of these 3 and applying t. Now, what we can do in the next step? Use the thing that t is a linear transformation.
One into t of 1 comma 0 comma 0
Yes.
plus 1 into t of 0 comma 1 comma 0
Yes.
plus 0 into t of 0 comma 0 comma 1.
Correct. Now the job
Which
is
is-
very easy because we know the value at a 1 0 0, 0 1 0 and 0 0 1. It is given respectively as 1 1 2 3 3 2. So what is the next step? 1 into
1 into 1 comma 1
Yes,
plus 1 into 2 comma 3 plus 0 into 3 comma 2.
correct. So now we just need to add this element. What we will get? 1 plus 2 is 3 and 4. Okay. So what we want to do is, we don't know the value at this point. We will write it as the linear combination of known values. And then we will apply the property of linearity of the linear transformation. And then we will use this result like T of 1, 0, 0 equal to 1, 1 and so on. So, and then we get the result. So in general, what will be like for one particular point, we got the value. Now, I am asking you how we can find T of XYZ. I don't know what is XYZ. I want to find the value of T at the general point XYZ. How can we write it? Just like this, how can you write T of what will be the explicit form of T of XYZ?
Simply we can equate the elements on both sides, ma'am.
Equate means how? Can you be more like?
Yes, ma'am. T of x, y, z can be written as a linear combination of T of x into 100 plus y into 010 plus
Yes.
z into 001. And simply we can equate xy coefficients on both sides, ma'am.
Okay, correct. So this is the same procedure as we did earlier. We are just writing XYZ as the linear combination of these known values because we know the value of T at 100, 010 and 001. So we are writing like this. And as T is linear, we can take it as X into T of 100 plus Y into T of 010 plus Z into T of 001. Now we will give the value. It is already we know what is 100 and T of 010 is 23 and T of 001 is Z into 32. Okay. So we will get X plus 2Y plus 3Z, X plus 3Y plus 2Z. So what here it says is, in the question, it is just given the map T on the basis element only, right? Only the value of T at basis is given, but just using that, we can say the value, like how the T is defined for all points in the R3. That means this T is uniquely determined by the value at the basis. If we know the value at the basis, we know we can uniquely say what is T like this. Okay, is it clear for everyone?
Yes, ma'am.
Okay.
Yes.
So next question is, the linear transformation T is given from the space R11, okay, R11 to R30. And it is given that it is 1, 1. Okay. And the options are Okay. So these are the 4 options. So can you say which one is correct answer? The question is T is a linear transformation from R11 to R13 and it is given that T is 1, 1. And these are the options. So what is the answer here?
Ma'am,
A,
either
ma'am. 13, nullity equal to 0.
Which one? Can you repeat?
Answer A, ma'am.
D. Okay.
A.
A. What is the reason?
The function is 1, 1. Kernel of G equal to singleton 0. So nullity G equal to singleton 0.
Okay.
Then rank of the theorem, rank of G plus nullity of G equal to 13. So rank G equal to 13.
Okay. There is a mistake. What is rank nullity theorem says? Rank of T plus nullity of T should be the dimension of this domain space. Okay. Everything else is correct. First of all, nullity, it is 1, 1 means nullity should be equal to 0. So nullity is 0. But rank of T plus nullity of T is the dimension. Like T is from V to U. If T is from V to U, then rank T plus nullity of T equal to dimension of V. Okay. So the first space. So here nullity is 0 because it is 1, 1. So since T 1, 1.
Then option D is correct.
Yeah, option D is the correct answer. Since T is 1, 1, nullity of T equal to 0. Okay. Only the 0 element, like 1, 1 means 2 elements is not mapping to the same point. Okay. Here it is 1, 1 means only 0 is mapping to the 0. So nullity of T is 0. And using the rank nullity theorem, rank of T should be 11 because rank T plus nullity of T should be equal to 11. Okay. Is this clear for everyone?
Yes, ma'am.
Okay. Now, next question is T is from Rn to Rn, the linear transformation. So we have a set of statement. So which of the statement says that T is a bijection? First statement, nullity of T equal to N. And the second option, rank of T equals nullity of T equals N. And third option is rank of T plus nullity of T equal to N. And fourth option is rank T minus nullity of T equal to N. So the question is, which of this statement A, B, C, D implies that T is a bijection? Any answer for this? You can go by option. Option, which option? Like you can go by option and discard, like if it is not a bijection, you can discard, and whatever remaining, for that we can go for a proof.
Option D.
Yeah, it should be option D. So why it is not option A? We will start from A.
If it is bijection means a nullity of T is 0. So they given N.
Bijection means, first of all, it should be 1, 1. If it is 1, 1, kernel contains only the 0 elements. That means nullity should be equal to 0. So, if nullity equal to N, it is not bijection. It is not 1, 1, hence not bijection. Now, what about 2? Why the second option is wrong? The same reasoning you can use, nullity of T equal to N. So this is not possible. One thing you can say like that. Otherwise also, here you can see they are saying rank T and nullity T, both are rank. And by rank nullity theorem, rank T plus nullity of T should be equal to N.
Yeah.
But here, rank T plus nullity of T will be 2N, right? So this B is not at all possible. Not possible. Like for any transformation, not just bijection, for any transformation, this kind of result is not at all possible. And what about C?
In C condition, we cannot say nullity of T is 0. We don't know.
Yeah, we don't know.
If it is
For any transformation, rank nullity theorem holds. So this holds for any transformation, not just for bijection. It can be bijection, cannot be bijection. So it holds for any linear transformation. And now, so obviously all the first 3 options are discarded. So the option 4 is the correct answer. Now, can anyone give the reasoning of that?
If T is bijection means we can say nullity of T is 0. Then the rank of T is equal to, obviously equal to N. So rank T minus nullity of T is equal to N means in that if nullity of T is 0, we can mention by bijection.
No. What you are saying is if T is a bijection, nullity of T equal to 0 and so on, so right? But the question is, which of the following statement shows that, or which implies that it is a bijection? So what I want is this condition. First assume this and show that T is a bijection. Means assume this and prove that nullity of T equal to 0. That is what you want to prove. Is that clear?
Yes, ma'am.
Okay. So using this condition, you should be able to prove T is a bijection. To prove T is a bijection, it is enough to prove that this nullity of T equal to 0. Okay. So now can you think how we can prove? Anyone can answer?
By converse.
Okay, I can give hint. T is any linear transformation. So the rank nullity theorem holds. That is this condition, rank T plus nullity of T equal to N. This we can use. And the given condition is rank T minus nullity of T equal to N. So we have 2 conditions now. Okay. Using these 2 conditions, can you think now?
We can add both, ma'am. Then we can get 2 rank of T is equal to 2N. So 2 get cancelled. So rank of T is N.
Yes, correct. So what we can say is by rank nullity theorem, what we have rank of T plus nullity of T equal to N. And given that rank of T plus, rank of t minus nullity of t equals n. So we add 1 and 2. Or we can subtract 1 and 2, whatever. So 1 plus 2 implies 2 times rank of t equal to 2n and rank of t equals n. So rank of t equal to n means from here we will get nullity of t equal to 0. Okay. It says that nullity of t equal to 0 says that t is 1, 1. And the rank of t equal to n. That means range covers the whole space Rn. Okay. So it says that t is on 2. Okay. Actually, for a finite dimensional space, like t from v to u to v and u and v are finite dimensional. And if we are proving either one of 1, 1 or on 2, we can say it is a bijection. No need to prove both actually. So here we are just mentioning both are like t is both 1, 1 and on 2. Hence t is a bijection. Clear? Any doubt in this question?
No, ma'am.
Okay, good. Now let's move to the next problem. So the question is, let T be a linear operator on So, T map, a linear transformation is given by, like operator means it is from same space to same space. Okay, it is just like same as linear transformation. Okay, so T is given from R3 to R3 and it is given like this. So the question is T invertible? And if yes, find the inverse of T. So, first of all, we will check whether T is invertible or not. For that, we just need to check whether 1, 1 on or on 2. Like any of the condition is enough. Okay. Let us first check whether T is 1, 1. For that, we need to check whether kernel of T contains any non-zero element or not. Okay. So we will find kernel of T. For that, we will equate T of x1, x2, x3 equal to 0. Okay. So what we will get is 3x1, x1 minus x2, x1 plus x2 plus x3. So we are finding the elements in the kernel. Okay. Okay. In between, if you have finding any difficulty or doubt, you just ask me. So we are equating by coordinate wise 3x1 equal to 0, x1 minus x2 equal to 0, and 2x1 plus x2 plus x3 equal to 0. Since 3x1 equal to 0, we can say x1 equal to 0. Okay. Since x1 equal to 0, here we can say x1 minus x2 equal to 0 means x2 equal to x1 and x1 equal to 0. So x2 is also 0. Here both x1 and x2 are 0 we got, and x3 should be equal to 0. Okay. So if t of x1, x2, x3 equal to 0, we got x1, x2, x3 is the 0 element. So what we are getting here is kernel of t contains only the 0 element. Okay. So nullity of t equal to 0. And what is rank of t? 3, because it is defined on R3 by rank nullity theorem. Rank plus nullity equal to 3. So rank equal to 3. So nullity of t equal to 0 means it is 1, 1. Rank of t equal to 3 means it is on to also. Like range contains all the space R3. So we got it is a bijection. Since t is a bijection, we can say it is invertible. So it is invertible. Okay. Now next we need to find what is the inverse of this t. So we got the inverse existed. So t inverse existed. Now I am assuming t inverse. Now I am assuming t of x1, x2, x3 equals ABC. Okay. I'm taking t of x1, x2, x3 equal to ABC. Now, what will be t inverse of ABC?
1 x2 x3 ma'am.
Yes, x1, x2, x3. That means if we have some random elements ABC from R3, we want to find what is t inverse of ABC. We just know that what is t of x1, x2, x3. So, using this star, we will find what is t inverse of ABC. Okay. Now, what is t of x1, x2, x3? It is given, okay, by definition, it is
3x1, x1 minus x2.
x1 minus x2.
2x1 plus x2 plus x3.
x2 plus x3. Okay. So, from here, I am equating this to ABC. Okay. Now, my aim is to find this value x1, x2, x3. Because this x1, x2, x3 is the t inverse of ABC. So, we will find this x1, x2, x3 in terms of ABC. For that, we need to solve each of the 3 equations. Okay. So, from here, what we can write is 3x1 equal to A and x1 minus x2 equals B. 2x1 plus x2 plus x3 equals C. Since 3x1 equal to A, what is x1? It is A by 3.
A
right?
by 3.
Okay. Now, what is x2?
x2 is b minus a by 3. Or
X2
3b minus
x2 is
A
x1 minus B. A by 3 minus B, right?
yes, ma'am.
x2 is x1 minus B. x1 is A by 3. So it is A by 3 minus B. And x3 is C minus 2x1 minus x3. So C minus 2x1 means 2 times A by 3. Okay. And minus x2. So minus A by 3 plus B. So it will come C minus A plus B. Okay. So T inverse of ABC is x1, x2, x3. and we got the values of x1, x2, x3. So how can we write T inverse of ABC? T inverse of ABC equals A by 3 minus B and C minus A plus B. Okay, this way we can find the inverse of the linear transformation. Is that clear?
Yes, ma'am.
Oh.
Yes, ma'am.
So okay, we will solve one more problem and then we can stop, I think. Okay, one simple problem we will solve. So here the question is A is a 9 by 9 matrix. Say vary overall 9 by 9 matrix. A is some 9 by matrix. 9 by 9 matrix. So how many different pairs of AB are there with nullity of A equal to A and rank of A equal to B? So it's very trivial question. Here you can see A is a matrix. So you can just like rank of A, you can see as the rank of the matrix. Okay. Rank of the matrix, you know, right? What is the rank of the matrix 1001?
2, ma'am.
Yeah, 2. And what is the rank of 2200?
1, ma'am.
But okay. So okay. So the rank means the same rank. Like you can see it A as the A as the matrix form of a linear transformation, or A as just the like A just as the matrix, and this rank is same as this rank. So anything you can see, and so as a matrix, what is the maximum possible rank of A?
9, ma'am.
-1.
Yeah, 9. So if rank is 9, what can be the nullity?
0.
0, because maximum like total is 9 only. So one possibility is A is nullity and B is rank, means 0, 9 is one possibility. That is 0 is the nullity, 9 is the rank. So what will be the next possibility?
1, 8.
1, 8.
1, 8, ma'am.
2, 7. Okay, right?
3, 6.
Yeah, like that it will go. Finally, it will go 7, 8, 8, 1, 9.
9, 0.
Okay. So total, okay, total 10 possibility, na? Okay. So total 10 possibilities are there. Correct?
Yes, ma'am.
So answer is option C. Okay. Any doubt in this question?
No, ma'am.
Okay. So, like in any of the concept or in any of the question, if you have doubt, now you can ask. Otherwise, I think let's stop the session today. Okay. So, shall we stop now? Okay, then let's stop for today and we will meet next week the same time. So thank you everyone for attending.
Thank you, ma'am.
Yeah, bye.
Yes,
See you.
ma'am. Thank you, ma'am.